Hi, I'm Chris Tomkins from Tigera. Thanks for coming to this talk. We'll be talking about the importance of modularity and support for multiple data planes in Kubernetes networking. I'll talk about what a data plane is, why Calico offers several of them, and how that can help you and your cluster stay agile today and tomorrow. There's plenty of great food for thought here, and I'm excited to dive in, so let's get started. So thanks for coming along. Here's today's agenda. The first thing we'll do is talk over an analogy which will help us to understand the concepts that come later. After that, we'll go over a couple of key concepts, modularity and coupling, and understand what they are and what they mean. Then we'll talk about control planes and data planes. We'll understand what those concepts mean and how they apply to network devices. Next, we'll talk about how all that relates to Calico. And finally, we'll look at what data planes Calico offers, how we can use them, and which ones might be most suitable for your environments. So the analogy first. I look at this picture and I want to relax in that garden, but sadly we can't right now. So instead, imagine that we need to repair this garden wall. One of the stones is crumbling. Where would you prefer that stone to be if you were responsible for repairing it? Would you want the stone to be at the top, in the middle, or near the bottom of the wall? We instinctively know that to repair that wall, it would be easiest if the broken block was near the top of the wall. That's because the blocks are irregularly shaped and joined together. So it might be difficult to remove a block near the bottom or in the middle without affecting the blocks around it, right? Okay, so consider a brick wall instead. How about now? Would it be easier or harder, and why? Intuitively, we know again that this wall would be easier to repair, and that's because the blocks are regular and the concrete is clearly defined, so we would be able to chip out a brick and remove it. We wouldn't need to take apart the whole wall. So we've seen that two different walls, depending on how they're built, one can be easy to repair and the other one difficult. So let's see how that relates to software. Well, software and protocols should be built in walls of blocks too, and this concept is known as modularity. So if we have a look on the right-hand side of this slide, you'll see there's a diagram called the OSI model, which is a very famous and important model for how computer networks transmit and receive data. You can see that it defines 7 layers, starting at the bottom, the physical layer, going up, the data link, network, transport, session, presentation, and application layers. You can see that when data is transmitted, it goes down the layers, acquiring extra headers at each layer. And you can see that when data is received, it goes up the layers, stripping headers off at each layer. So the OSI model is clearly modular. It looks like a brick wall. However, that modularity is sometimes implemented better than others. So let's consider a success case first, layer 1 of the OSI model. And now layer 1 defines the physical network and the way that the bits are transmitted on that network. So, for example, electrical standards of cables, pinouts of how cables are connected, media types, so that could be copper, fiber optics, or even the air for Wi-Fi, and modulation, so that's how we modulate data onto the physical media. All of those vary depending on the layer 1 implementation. And yet, when a user is using the internet, they don't need to care about any of those details at layer 1. And that's because layer 1 was successfully designed to be very modular. The higher layer modules don't need to care about the implementation of layer 1. In fact, layer 1 is so brilliantly modular that there was even an RFC, or request for comment, RFC 1149, which made a joke about the idea of transmitting IP over avian carriers or pigeons. Now let's contrast that with layer 3 of the OSI model. Layer 3 is responsible for IP addressing. You've probably heard of IP addresses, IPv4 addresses, and IPv6 addresses, and you probably know that IPv4 addresses are being exhausted, and we're trying to move to IPv6. Now that migration has been going on for a long time already, and it will continue to go on for a long time before it's completed. And the reason for that is because IPv4 is too tightly coupled to the blocks around it. So, for example, IPv4 and IPv6 have different broadcast behavior. Broadcasts are also relevant at layer 2. So there's a crossover between layer 2 and layer 3. Similarly, browsers need to behave differently for IPv6 and IPv4 addresses. So that means that IPv4 and IPv6 cross over slightly into layer 7. And another example, name resolution behavior, which should traditionally be at layer 7, actually behaves differently between IPv4 and IPv6. So again, there's some ambiguity between layer 3 and layer 7 in the stack. So unlike layer 1, which was successfully designed to be very modular, layer 3 is too tightly coupled to the blocks around it, and it's very hard to change your layer 3 implementation without affecting the other blocks. So we understand modularity and we understand tight coupling. Consider these two pieces of fictional enterprise software. We've got a pizza store system with an ordering stack and a kitchen stack, and we've got a car rental system. There's a front end and an inventory module. Now, the pizza store system has a strictly defined interface between the ordering software and the kitchen software. That means that in order for those two pieces of software to communicate, they have to send strictly defined messages. You can consider it like two teams in an organization that have to pass notes on formal headed paper before they can share information. The car rental software, in contrast, the two pieces of software, the two modules, can reach in and take data from each other. So the car rental software is tightly coupled and the pizza store software is loosely coupled. Loose coupling with a strictly defined interface makes the software components easier to fix, troubleshoot, and replace, because provided you don't affect the external behavior of a module, then you can just replace the module as long as you don't touch the strictly defined interface. So we need to think about modularity and coupling. And generally, loose coupling is preferable to tight coupling, although there are some advantages to tight coupling in specific cases. But for our purposes, we prefer loose coupling and modularity. So how does this apply to networking software? Well, in networking, there's a tradition of a node or device having a control plane and a data plane. So before we get into that too much, let's look at the diagram on the right. You'll see there's a blue outline, and that blue outline is a network node. A network node might be a router or a switch or a Wi-Fi access point or a VM host or a container host. You can see that there are two adjacent network nodes. Within the network node, there's a software concept or module called a control plane and a software module called a data plane or a forwarding plane. The control plane sends data to other control planes, and that's represented by the green arrows on the diagram. In fact, that data goes through the data plane as well, but for simplicity's sake, we show it between the control planes on this diagram. And the red arrows represent user network traffic. So that's traffic sent between the data plane nodes. The control plane and data plane exchange data. The control plane is responsible for programming the data plane. So the control plane is responsible for figuring out what's going on in the network, achieving consensus, for example, understanding the topology of the network and understanding when routes appear and disappear in the network or when there are multiple paths between nodes. The control plane is responsible for programming the data plane to make forwarding decisions. The control plane is typically implemented on a general purpose CPU, just like the one in your laptop or in your desktop PC. And the reason for that is because it manages complex device and network configuration and state. So this is a sophisticated bit of software which has complex requirements and requires the equivalent of a PC to run on. If you're familiar with routing protocols on the internet, such as BGP, OSPF, or ISIS, these are implemented in the control plane. So the control plane's job is to understand the network topology and to maintain a view of that topology. It has other functionality too, but the key points are the control plane is sophisticated and complex, and that's by design and necessary. How about the data plane in contrast? Well, the data plane is instead responsible for processing transit traffic going through the device. For example, all those cat videos on the internet, all those YouTube videos, emails, video games, all of that is data plane traffic, the traffic shown in red on the diagram. There's lots of it. And so the data plane needs to be able to use hardware acceleration features of the network node in order to be able to forward the volume of data that's required in a modern network device. Some devices nowadays are forwarding at 40 gigabit or 100 gigabit. It's very difficult to achieve that without specialized hardware. So the data plane should be designed to be the simplest possible implementation of the required packet forwarding features. Why the simplest possible implementation? Well, we don't want to do extra compute work beyond what is strictly necessary to forward the data. But we do have a required set of packet forwarding features, and the data plane has to implement those. It implements a fast path for traffic. One good example is MPLS. MPLS has become extremely successful in service provider networks, and that's because it's a perfect match of technology and implementation. Its job is to forward traffic fast, and so it was designed to perform minimal packet processing on each packet. MPLS networks simply use a stack of labels, and they reduce the complexity of IP forwarding by getting rid of variable length subnet masks, which allow you to have networks of different subnet mask length, for example, a /24 or a /28. Those are gone in MPLS, and there's no checksumming in MPLS. All of this simplification allows the data plane for MPLS to be very fast, simple, and effective. MPLS was a good example of identifying the key requirements and implementing only those requirements. Okay, so now we understand about modularity, about tight and loose coupling in software. We understand about control planes and data planes. Let's talk about Calico's data plane support. Now, Calico was designed with a 4-tier wall from day one. Modularity and loose coupling come by design in Calico, and that has given us a huge number of advantages. We'll go into some of those now. So the 4 tiers in Calico are, or I should say the 4 modules, are the data model, the Felix calculation graph, the data plane driver, and the data plane itself. So the data model defines the custom resources used to enable Calico. The Felix calculation graph is the control plane here that makes the smart decisions. Then there's a data plane driver, which is a simple and minimal driver for programming the data plane. You can think of it like the pinky purple line that we showed in our diagram before. It sits between the control plane and the data plane, and the data plane itself, which is responsible for forwarding packets through Calico. So note again that the Felix calculation graph is similar to the control plane, and the data plane here is responsible for forwarding packets. The data plane driver can be considered like a translation layer between the two. Today, Calico offers 4 pluggable data planes. If we look at the diagram on the right, you'll notice there are 3, not 4, and that's because one of the ones I'll talk about today is in tech preview status and therefore isn't shown in this diagram yet. So the Calico cat in this diagram sort of represents the control plane. Underneath that, you can see the data path or data plane, and you can see the 3 options: Linux iptables, the Windows host networking service, and Linux eBPF. We'll talk individually about each of those data planes in a moment and what they offer us. We also have VPP or vector packet processing, which is a 4th data plane currently in tech preview. We'll talk about that too. So why do we want 4 data planes? Well, by implementing data planes separately, we can reuse the sophisticated control plane code. We noted that control plane code is sophisticated by design, so we don't want to rewrite that code. We want to write it once and get it right. It also allows the data plane code to be specialized and minimal, which makes it easy to audit, easy to troubleshoot, and easy to fix. And lightweight code tends to be faster. But each data plane can focus on a targeted feature set. It might be that you have a requirement for IPsec encryption, or it might be that you have a requirement to support Windows nodes. Different data planes are suitable for different purposes. This allows us to future-proof. If our customers are finding particular value in a particular data plane, we can iterate on that data plane to provide extra support. If a new technology appears on the horizon, we can implement a new data plane to try that technology out, whilst continuing to support the features that we always have in our existing data planes. It allows us to be future-proofed and agile. Not only that, it allows you to be agile because you can switch data planes quite effectively as your requirements change. So by supporting different data planes, we allow the data plane to be the right tool for the job today and tomorrow. So the Linux iptables data plane is our oldest data plane. Therefore, it's heavily battle tested. It's been used in production for a long time on many clusters. It still offers good performance, and it offers great compatibility across a wide range of environments. It also has wide support. It doesn't have high requirements for example, the kernel version of the node. The Windows Host Networking Service Dataplane allows us to deploy Windows containers and to secure them. And it works in any cloud computing provider or on-premises. The third option, our Linux eBPF dataplane, is our newest dataplane. It scales to higher throughput, it uses less CPU per gigabit, and it has native support for Kubernetes services. That means that when you use the eBPF dataplane, you don't need to run Kube-Proxy in your cluster. The Kubernetes services are instead implemented in the eBPF dataplane. That confers some advantages. It reduces the first packet latency to services, it preserves the external client source IP address all the way to the pod, and it supports direct server return for better efficiency of traffic transmission. It also uses less CPU than Kube-Proxy. We'll talk a little bit more about these advantages on a forthcoming slide. So eBPF has history back to 1992, when it was known simply as Berkeley Packet Filter, and eBPF is a re-implementation which has many benefits. In short, it implements a virtual machine embedded within the Linux kernel, which can run small modular bits of code for particular purposes, such as debugging or networking. The code is statically checked to make sure that it's secure and then executed. So Calico uses eBPF. So let's have a look at how forwarding works with Kube-Proxy without Calico eBPF. So in this diagram, we have two Kubernetes nodes and an external client. The external client wants to talk to a service in the cluster. So he hits an IP address, and the IP address is assigned to Kube-Proxy. So Kube-Proxy responds. Kube-Proxy needs to forward the traffic on to a service pod. So the first thing it does is destination and source nats the IP addresses in the traffic and forwards the traffic on to the service pod. The service pod sees the ingress node as the source. So notice that the service pod doesn't get to see the IP address of the external client. And then in step 4, the traffic goes back through the original Kube-Proxy session, and the source and destination IP addresses are put back to normal and forwarded to the client. So notice a couple of things here. The traffic has to go back through the Kubernetes node hosting the Kube-Proxy, and the service pod never got to see the external IP of the client. That can be a problem if you need to do logging or filtering of the external client IP. So let's contrast that with what's possible with eBPF. We still have the same two Kubernetes nodes at the bottom and the same external client. But notice that now there's no Kube-Proxy. So step 1, the external client sends the traffic to the Kubernetes node hosting the service. The eBPF program spots the packet, makes a load balancing decision, and forwards the traffic on to the other node. Step 2, the BPF program in the second node does a destination NAT to the pod's IP. Step 3, the pod gets to see the real source IP of the external client. And step 4, the pod responds. Notice that the response goes directly to the external client. Step 5, if the network allows, the packet goes back directly. Otherwise, it returns via the ingress node. So the important differences here with the eBPF dataplane are the eBPF dataplane adds functionality to allow direct server return and to allow source IP preservation. So the final dataplane we'll talk about today is the VPP, or Vector Packet Processing dataplane. This is a dataplane that's in tech preview. It was developed by the FDIO group, and it offers a very high performance dataplane, particularly with IPsec encryption. It also has native support for Kubernetes services with the same advantages that we just discussed for eBPF. VPP is part of the FDIO project, which is part of Linux Foundation Networking since 2016. It's an open source extensible framework, and it's adapted from Cisco's VPP technology, which is production code running in shipping products. So in particular, it offers amazing IPsec performance and great WireGuard performance too. So we talked about software modularity and the importance of it. We talked about tight and loose coupling between software components, and we talked about multiple data planes, both generally and in Calico. So supporting multiple data planes in Calico achieves future-proofing. We can create new data planes to take advantage of new technologies. It provides agility for us because we can spend more or less development time on the data planes that our users find most value in. And it provides agility for you because it allows you to switch data planes to provide the networking functionality that your cluster needs. Supporting multiple data planes allows you to use the right tool for the job at hand for your cluster.